You believe it?
Yeah.
Okay, here's what I want you to tell me. If we're going to talk about describe a graph, we're moving into, in chapter 3, we start to get into analysis, functional analysis, using calculus. So we want to be able to look for interesting places on graphs, and we want to be able to describe graphs efficiently. One thing that it's useful to do is to talk about a function being smooth, literally. That's the mathematical term.
Smooth with the SL?
Smooth.
Smooth.
Is smooth. Now, what do you suppose a smooth function would have to
No cusps.
be like? Oh, okay, yeah. Can't have any cuts. Can't have any sharp corners.
Or breaks.
Right. It's smooth, meaning if I were to, rub my hand along the graph, I'm not going to get cut anywhere. Right. It's nice. It's smooth. Okay. Now, as a part of that, not only can not have any cusps, doesn't it also probably need to be continuous?
Yes, it does need
Right. So if I want to say, if I've got some function, and I say that between points A and points B, the function is smooth, then that means, right, doesn't it make sense that means that when I'm graphing the function, when I get to point A, between point A and point B, not only do I not pick my pen off the board, I'm not making any jagged edges. Right? Okay, so now, mathematically, what are the conditions that would produce that? Continuity we got. Right? So one ingredient must be for f of x to be smooth on this closed interval. One thing that must be true is continuous on the interval. Right? So my pen's on the board all the way from x equals A to x equals B. Outside of that, we don't care. Right? Now, what about the non-jagged part? The part that makes it. Yeah. No. Okay. We can't have cusps. Now, where would cusps occur? One example would be an absolute value function. That's one of the infinite examples. But I want to know, rather than rattling off individual specific examples, I want you to tell me what's the mathematical condition that would have to be met for there to be no cusps or sharp corners. And sometimes, logically, it's easier to ask the question, well, where would they exist than where wouldn't they exist?
Sudden change.
Yeah, sudden change. Now, okay, change, that's a topic we've talked a lot about. Where did we encounter the concept of a cusp or a sharp corner? Where did that come up? Well, absolute values was an example, but it was a topic we were talking about. Differentiability, that's it, exactly. We talked about the places where a derivative doesn't exist. And we said that one place a derivative doesn't exist is where the function is discontinuous. One place it doesn't exist is where we get these wacky vertical asymptotes. And the other place it doesn't exist, and then one place is where we get a vertical tangent line, right? But probably the most important of all those, maybe not the most important, but the most common at least, is it doesn't exist at a sharp corner, right? Where the derivative suddenly changes from one point to the next. So for example, if we said something like this, you might recall. We said that if we've got some function that's doing that, and then all of a sudden it does that, an ant walking towards the intersection on the blue curve is going to sense a negative slope there, right? Right until he gets to the point. An ant walking leftward along the red curve towards that intersection is going to sense a negative slope. And so when those two ants meet on that intersection point, they can't agree, right? So neither one of them could have priority. Neither one of them is more right than the other, and so the consequence is there is no derivative, right? The derivative is undefined there. So it's a matter of differentiability. If we want to have a function that is smooth, meaning there are no cusps, then there better be no places where the derivative is undefined, right? It better be take the derivative of all, meaning differentiable, everywhere on that interval. So there's the second ingredient. It's got to be continuous and f of x must be differentiable on, now, we don't care about the endpoints. We just care about the points in between. So it's going to be the open interval from A to B. Okay. We don't care if at the endpoint it did this. What if it was only defined from there up to there, and then everything else wasn't there? That would be smooth, right? I wouldn't have derivatives at the endpoints. Wouldn't make any sense to have a derivative because there's no function left to the left of the endpoint to use to calculate a slope, right? But we do care that on every interior point, there are no cusps. Make sense?
Yep.
The book doesn't use the word smooth. What the book always does, and where this comes up, is this guy. Okay, I want you to tell me, here's another. Explain how this could happen. Let's say I want to, if
Yeah.
then what? If f of x is smooth on the interval from A to B,
Then it is.
if f of A equals 0 and f of B equals 0, then what interesting has to happen?
Has to cross 0. What?
Now we could, this is A, let's say. There's A, and there's B. And so the function, the value f of A, we said, is 0, right? So there's the point A, f of A. F of B is 0, so there's the point B, f of B. The function is smooth, continuous and differentiable. So something interesting has to happen on that interval.
What do you mean by interesting?
Something interesting. Something is guaranteed to happen. I want you to tell me what's guaranteed to happen.
Curves.
What's got a curve? Okay, that's part of it. What was that?
Either change from positive to negative.
The what does?
Positive.
You're on something.
The points.
Well, it could go negative and then positive.
I said either or.
It only
I
crosses.
mean, so you're saying it's got to do something like this?
Well, not necessarily.
Okay, good. So it doesn't have to do that.
Yeah. But I mean, at one point, there's going to be
A what?
A change in
gravel,
direction.
a change in direction.
There's got to be a turning point. Now, what are some ways to describe that? What you're saying is there has to be, you guys were skirting around it, but
Parabola.
something like that has to happen. And the interesting point there is right up there. What's happening? It's a maximum. Okay, so right, it's a place where we could describe it as a maximum, but there has to be a place where turning point, maximum, what's going on at that point, regardless of what I call it.
Changing at 0.
The what?
Changing at 0.
The slope is 0, meaning the derivative is 0, right? So there has to be some point, at least one point on the interior, call it point C, where f prime of C is 0. There could be more than one, right? For example, what if the function did this? It could do that, and then I got a whole bunch of them, there, right? I get a bunch of them, but there's guaranteed to be at least one place where the derivative is 0, which means a horizontal tangent line, which means a turning point, a minimum or a maximum, right?
Why does it have to have a derivative?
Okay, well, how could it not? If the
Why
function
can't it be
is
a line?
smooth,
Yeah, why can't it just be a line?
well, if it's just a line, then the derivative is 0 everywhere. And every point is, right?
That'd be smooth.
Yeah, it's smooth, sure. That's not a very interesting case. That would be the one case where you could say, well, what about that case? But even in that case, there are an infinite number of places where the derivative is 0.
So it doesn't have to be
Every point has a horizontal tangent line.
And the red line, I thought like the definition of maximum was
It's the highest point. Yeah.
Okay, no, now we got to be careful. Are we
Relative.
talking absolute maximum or relative maximum?
Yeah.
When we talk about a turning point, a peak or a valley, which kind are we talking about?
Relative.
Relative, right? We know that even though this may not be the highest mountain in the range, it's still a mountain, right?
Wait, so that means every point could be a maximum or minimum?
No, that point can't right there.
No, but the point next to it is higher than it.
No. Okay, but for it to be a relative maximum, that means that relative to the points around me, I'm the highest. So locally speaking, now that doesn't mean that out there someplace there couldn't be another place higher, but relative to the points immediately next to me, not that there's such a thing, but if I take a step of any size in any direction, vanishingly small step, I'm always going to be moving down from that point in either direction. Does that make sense?
Yeah.
So topologically, when we talk about a maximum, we're talking about a relative maximum. An absolute just means on some given interval,
The highest.
what's the highest point, which could also be an endpoint, right? Okay. So that's, do you see what that's, by the way, that's called Raleigh's theorem. Raleigh's theorem just says if a function is smooth on an interval and the endpoints both have values of 0, then someplace in between there's guaranteed to be a turning point.
It's spelled Raleigh.
R-A-L-E-I-G-H.
Oh, wow.
Wrong.
Way to be wrong.
It's Raleigh's theorem. Okay, now the way they say this in the book, they're always going to say, they say smoothness, they always say continuous on the closed interval and differentiable on the open interval. But it's nice, the book doesn't do it, but it's nice to be able to use that word smooth instead, because it's double whammy, you get 2 for 1. You get the fact that it's continuous and not jagged and differentiable. Now, one thing that's helpful when we talk about differentiability, if it's differentiable, if the function is differentiable, then that means just that the derivative exists, right? Because think what differentiability meant. We found the places where the derivative didn't exist, where it wasn't defined. Those were the ones where it was either the infinite peak or valley, the asymptote, break in the function, vertical tangent, or corner. And then of course we get oscillating, then the function is all messed up, right? Then you're done. Then you can't pin it down, and a lot of stuff doesn't work. So if we wanted to try to figure out where a function is differentiable and where it's not, the function, what we have to analyze is not f of x, but its derivative, right? So us saying that f of x is differentiable on this interval is the very same thing as saying, what about the derivative? F prime of x exists. Yeah. Exists and is continuous, right? That make sense? Okay. So it exists on AB. So that's how we're going to find the places where we don't get differentiability or we're going to highlight, we're going to take the derivative and see where we have problems, right? Yes.
Are you recording this?
Yes. Yeah. Okay, so now Raleigh's theorem is interesting. Raleigh's theorem is interesting, but we can make it more interesting if we tilt it. Instead of pinning ourselves down to say that f of a has to be 0 and f of b has to be 0, let's not do that. That's one specific case, but let's try something a little different. And we can sort of abandon Raleigh's theorem because Raleigh's theorem ends up just being a generalized case of a better theorem, a more general theorem, or as a specific case of a more general theorem. And so, how do they say it in here? Okay.
So this is good stuff.
Yeah, this is good stuff. So what we want to do is we're going to tilt this thing, and we're going to say, okay, now we've got some smooth function. So f of x is smooth on AB, continuous and differentiable. And this time at A, we're going to say that we're not going to pin A down. We're just going to say, what's going on? Is there an earthquake here?
Somebody's wiggling the other desk. No.
Not really. What is that?
Somebody's doing this.
No, it's doing it really hard.
Yeah, that's from Scott.
There you go.
Oh, somebody's walking up there. See a shadow.
Oh, yeah, there was somebody up there.
Serious?
Yeah.
Are you serious?
Yeah.
Maybe we should call someone.
Just taking a stroll.
Yeah, there was another
Well,
question.
that has them
What's that?
Yeah, it moves your screen.
Wow. I think I've wiggled around enough that
Wow.
Okay, so now what about this? So if the function is smooth on the interval between A and B, then what could we say about that? Oh, they did. Check that out.
Did you know that?
No.
That's so observative.
What can we say about this one?
Yeah. What do you mean? It's the same thing except for
Same thing. Now look at Raleigh's theorem. What did we do for Raleigh's theorem? For Raleigh's theorem, we said that if we start here and end there, there's got to be a place in between where we have a horizontal tangent line, right? Now notice that the secant line connecting points at A and B is also horizontal, right? So we've found, one thing we found is just, it's interesting to know that there has to be a turning point, but it's not coincidental that the secant line and the tangent line are parallel. They have the same slope at that point, right? So now what if we tilt Raleigh's theorem? What is it that we're probably going for here?
Just draw a line.
Well, we could, but if I draw some random function, smooth function, like so, where is there a point that might be of interest there? Keeping in mind that here's our secant line.
change of slope?
Okay, so you want the you want the maximum tangent.
Well, not necessarily. There's no guarantee. Maybe I better show that to you. But you better tell me why. Okay, somebody maybe draw a picture, but I want you to come up and connect these dots. There's A, there's B.
You got this.
Does there have to be a turning point between those two?
No, it could be segment.
Right? Or even if it's not straight. Sure, it could go like this, right?
That's what I meant.
Something like that that's not straight and yet doesn't have a turning point, right? Agreed? So that's not what we're going for. That's not what we want. But the secant line, the slope of the secant line, remember, that gives us the average rate of change of the function. That tells us between x equals a and x equals b, the average rate of change was the slope of that. Sometimes the rate of change was a lot steeper. Sometimes it was a lot more shallow. But the average rate of change is that, the slope of that red line. Okay? The instantaneous rate of change of the function at any point we take is the slope of the tangent line, right? So for example, if I draw in right here, the instantaneous rate of change is greater. The slope is bigger, right? Right here, the slope is less. But what must happen between those two endpoints?
Must be a maximum.
I don't care about the maximum. There doesn't have to be a maximum. It doesn't have to be a maximum, but something has to happen. There has to be a relationship between the instantaneous rate of change and the average rate of change. The slope of the secant line,
Must change. That's what they also measure for vice versa.
what do you think? What has to happen there? How? In what way is the function necessarily at some point related to the slope of that secant line, that average rate of change?
Has to be that slope at some point.
At some point, doesn't it? Right? If the function is smooth, and I can't make it jagged, then if the function starts off with a greater slope, it's got to end up with a lesser slope. It's got to turn somewhere, right? Make sense? And so somewhere in between, because it's smooth, and every possible infinite value of the slope in between that and that has to be realized in between, right? You can't skip over some values of the slope. It's smoothly transitioning. There has to be a point in the middle, at least one point, maybe more, where the slope of the tangent line is the same as the slope of the secant line. Now, why is that important? What that tells us then is for any smooth function, physical or not, there has to be a place in between A and B where the instantaneous rate of change is the same as the average rate of change. Now, that's important. For example, what if we were going to get in a car and we were going, if we're getting in a car and we're driving, our speed, our rate of change of position has to be smooth. There's no way that the car can ever just instantaneously go from 0 to 60. It's got to go through every speed in between, doesn't it?
Good car.
Right? I mean, that would, if it did, the car would be infinite acceleration, and everything would just be, you know, atomized. It would, everything would be the slope would squeeze you into just a gooey mess on the back of the car
Unless there's.
because the acceleration would be so great. You can't do that. You can have a big acceleration, but still it's continuous, right? So then what I'm going to tell you is that if you were going to, let's say you were going to start from rest, and you were going to put the pedal to the metal, and you were going to travel a quarter mile in 15 seconds.
Oh, it's weak.
Okay, what's your average speed in good old miles per hour?
Quarter of a mile,
So I did a quarter of a mile in a quarter of a minute.
So 1.
So it's 60, right? My average speed is hang on, did I say I ended at that? Yeah, I said, okay, I said I traveled, what I said was this, I traveled, okay, say that again.
Now you're trying to remember.
Yeah, what did I say? Hang on.
It's like a mile and 15 seconds.
Right.
Okay, half a mile in 15 seconds. Okay, so then, assuming I accelerate the whole time,
It's really slow.
I've got to be going pretty fast at the end of that, don't I?
No, that's really fast.
Right?
Fairly fast, yeah.
I can't go faster, I mean, I have to be going faster than 60 because my average speed is 60, right? So I might be going 90, I might be going 100, who knows?
120, 150.
That's, I'm going pretty fast, I got a good car, I guess. If I'm going to get through that quarter mile in 15 seconds, which would be pretty fast, I don't know, that'd be...
Drag racing.
Constantly accelerating, you gotta go faster than 120 at some point. So
That's-
you're going really fast.
So my point is this though, if my...
Hey, would you stop it?
If my average speed for that quarter mile track is 60 miles per hour,
Then you half mile.
Okay.
the mean value theorem,
So you wouldn't just stop, you'd be like, you'd be
Just whenever you're ready.
the mean value theorem tells us that because the speeds that I'm traveling
Because you're starting at 0.
represent a smooth function, I have to at some point be going 60 miles an hour. It might seem intuitively obvious to you, but this is the proof right here. This is what proves that mathematically, right? There's no way for me to start off with a slope, right, a rate of change of position of 0, and travel through a quarter mile track and end up with an average of 60, and at some point not go through 60. It doesn't specify how fast I end up. If it was uniform acceleration, I would end up going 120, right?
Yeah.
And then exactly in the middle, I would hit 60. But there's no guarantee that the car is going to accelerate that uniformly. It might start off accelerating a little faster, and then after a while, there's wind resistance builds up, and it doesn't accelerate as fast, a little more drag. And so it might start off accelerating faster and then kind of peter out. But if we look at the profile of the graph, it's got to look like this, right? If I'm looking at position versus time. So there's position, call it X. There it goes, versus T. If this is quarter mile,
Yes, quarter mile.
okay, 0.25 miles, and this is 15 seconds, then I know that I'm going to go from there to there, right?
So,
Right.
okay,
When 15 seconds is elapsed, my car is that far away from the starting point. If this is tracking how far I've moved and this is tracking time, it might be that I start off with a bigger acceleration than I end up with. But at some point, that average rate of change, which I can calculate, the slope of the secant line is just rise 0.2 miles over 15 seconds. We'll call that 0.25 minutes, 1 mile per minute, which translates into 60 miles per hour if I want to change the units, right? So if that's the slope of that secant line, there's got to be a place in there. In this case, it's right about yonder, where I'm going through that speed. Now, if the halfway point is right there, we could say that if we start off accelerating faster and then our acceleration declines, wouldn't I get to that before the halfway point somewhere? Maybe my car is does this instead. Maybe it starts off, I'm just going to kind of ease into things, and then I'm going to give it a burst of speed at the end. In that case, I wouldn't hit that point until maybe I'm a little bit past the halfway point. But somewhere in there, I got to hit it. Maybe, if I'm really tricky, I even do this. Maybe I'm going to do something where I do something like that. I might hit it more than once.
Possibly. Hitting some sand pits.
Make sense? Okay, that's the mean value theorem. There's not that much to it. What kind of math problems do we do with the mean value theorem? Well, funny you should ask. Problems like this.
Relatively challenging one.
That's what we're going to do. We're going to say something like this.
Is this the what?
Yes. Apply the mean value theorem to find all values of C on the interval from A to B such that
That's the first word.
that's mean value theorem, sorry. Such that
Not that one. That is a really cool looking one. Maybe that one.
okay, we got to find all the places where that happens. We want to find all the places where the value of the tangent, slope of the tangent line, right? The slope of the function equals the average rate of change. That's just saying slope of the secant line, isn't it? Final value minus initial value over change in x, right? If I want to go back to my pretty picture here, if I wanted to find the slope between, well, actually, let's go back to one more. Let's go back to there. Let's call that A and that's B. If I want to calculate the slope of the secant line, that's just a slope triangle, isn't it?
This is
Right? This distance right here, the delta x is just B minus A. Delta y is just, there's my point, B, f of B. There's my point, A, f of A. So that's just the difference in the y values. F of B minus f of A, right? Rise over run.
Yep.
There it is. Slope of the secant line. All I've said is where m tangent equals m secant. Right? So now that's what we want to find. All the places where that happens on the specified interval. Okay, so here's the problem I'm going to give you. Let's say specifically that f of x equals, let's start easy. Let's say f of x equals x squared on the interval from -2 to 1. Okay? So if we were to draw this thing, we don't have to, but if we were to draw it, if I'm going from -2 to 1, with my parabola, at -2, what are the coordinates?
-2.
Well, no. If my function is x squared.
Oh.
Yeah. Okay, so -2, 4, right there. And 1, 1. Okay. I want to find all the places where the slope of the secant line,
Is what?
right, is the same as the slope of the tangent, or the slope of the curve, right? Slope of the tangent line. We can sort of see where that is. It's right about, I don't know, right about there it looks like, huh? Approximately. But we want to find where. Exactly. So let's do the math. What is this value? That value is just going to be f of b, that's 1, right? F of 1 minus f of -2 over 1 minus -2. So that's 1 minus 4 over negative 3, right? Everybody see that? 1 minus negative 2. In other words, I've traveled and going from there over to there. I've risen by negative 3 and run by 3. That's all we said, right? F of 1 is 1. F of negative 2 is 4 over the change in x. Okay, so I want to find the places where we get a derivative equal to negative 1. Well, we want to know when f prime of c is that. Well, what's the derivative of our function?
2x.
Right? So we want to find all the places where our derivative, 2x, equals negative 1. Thank you.
Oh, yeah. Is that 1 minus negative 2 is 1 minus 4?
Well, no, here. This is the derivative function.
Oh.
Nope. Right above your big 2. In the cornered box. Where you get the f of x. Yeah, right there.
Okay.
One down. That 1 minus 4 right there. Up, right there. Bingo, bingo. Where'd you get that?
How did I get that?
That's squared, so it's positive.
The f of negative 2 is 4.
No, we're saying the.
Right. So it's right. So negative 2 squared is 4. 1 squared is 1. Right? So f of 1, if that's our function, f of 1 equals, f of x equals x squared. F of 1 is 1 squared. F of negative 2 is negative 2 squared.
Gotcha.
Right? I made that. It's
I
kind of
didn't
fancy.
see the hand reference there. I didn't.
Okay. All right. Does that make sense? Okay. So then we want to know where our derivative equals negative 1. What are the answers, or answer in this case? X equals what? Negative 1/2. And we want to know the point. Is that what we want to know? 2.9. Okay. No, we just want to find C, all the values of C. So we found it, negative 1/2. Let's try another one. One more. If we have time for one more, I'm happy. How about
5 minutes ago.
we can do it. Yeah, it's no big deal. Okay, let's try this. Let's try, okay, f of x equals x plus 1 over x on the interval from 1/2 to 2.
Your dean.
Pretty much. Right now.
Yeah. Actually, you know what? I want to do a different one. I want to do one. I think that'll work, but I know this one will work better. Let's try this. F of x equals 5 minus 4 over x on the interval from 1 to 4. Whoops. Okay. So we want to find all the places that satisfy the mean value theorem. We want to find all the places, all the values of x, which we'll call C when we're done. All the values of x where the derivative equals the average rate of change on that interval. Okay? So what's the derivative of our function? Derivative of 5 is 0. This is the same thing as saying negative 4x to the minus 1, right?
That would be
So
correct.
what's the derivative of that then?
Negative 4.
Negative x, good. So 4x to the negative 2, right?
Yeah.
So same thing as 4 over x squared.
Bingo.
Right.
Okay, there's our derivative. So we want to know where is our derivative equal to the average rate of change? Where is that equal to f of 4 minus f of 1 over 4 minus 1? 3. So what is f of 4? If I plug 4 in for x, what do I get back? 4.
Oh, okay.
4, sure. Okay. So 4 minus, what's f of 1? 1. Over 4 minus 1 is 3. So that's just 3 over 3. That's 1, right? So there's the equation we're solving. When is 4 over x squared equal to 1? How do I solve that equation?
4 squared 4 is 2.
There's my hand. 2.
It's 2.
Okay, cross multiply.
Answer is
Cross multiply, and that's going to give me x squared equals 4. So,
oh, you square root here.
okay, so then x equals
2.
plus or minus 2. Okay, plus or minus 2. But the question specifically wants to know, find all values of c on our interval. Now,
it's
are
only
both
2.
of those,
Like I
good.
said.
Negative 2 is outside our interval, so we can discard that one. We don't care about that one. The correct answer, if you put them both, it's wrong. The correct answer is only 2, because that's the only interval that exists between 1 and 4 inclusive, right? So, x equals 2. Make sense? Okay. All right.
Glad we got
Good
through
stuff. Good stuff.
Is that 3.2?
3.2 is in the
Is it up?
bag.
So everything is due Thursday?
Well, I'll let you guys catch your breath a little bit here. 3.2. I won't make the chapter 3 stuff due until about next month.
No, I mean like all the tests and everything right at the end of Thursday.
Is 3.2 up?
Well, all the like assignments are due.
Only we've already done it, not 3.1.
No, but I'm talking like 2.6.
Oh yeah, those. Right. I think most people are.
I have 2 more questions on 2.6
Okay.
that I need help with. I can't figure them out.
Okay.
It's just 10% of our grade, isn't it?
Yeah.
Yeah, I don't think I've done very much.
No, that's what Mr. Johnson always says. Like, you say all the time, what would he even use? Watch that.
He said a rhetorical.
One more problem on the test.
Okay.
Are you kidding me? That's impossible. Is there any possible way you could ever feasibly?
No, really, there's not, because
you don't know his ID. Please come to the office.